Welcome to the Deep Dive. We crack open compelling research and, well, distill it into insights that hopefully make you smarter. Today we're getting into a challenge that I think many of you face, building predictive models that are really effective. Sometimes just relying on simple linear regression, especially when you're swimming in just tons of data, it just isn't quite enough. It can feel like you're leaving performance on the table maybe, or wrestling with a model that's just too complex to really get your head around. So our mission for this deep dive is to arm you with some powerful methods for improving those linear models, moving well beyond ordinary least squares. We're going to unpack techniques to help you pick the best model best for prediction accuracy and for interpretability. We'll look at three major classes of techniques and then really dig into how you choose the optimal model. Make sure you get maximum insight without, feeling totally overwhelmed.
Exactly. And linear models, they're a fantastic starting point, right? They're foundational in statistics because they offer clarity, you can interpret them, and often they have surprisingly good predictive power. So our discussion today is really about the sophisticated ways to make these already good models even better, pushing their capabilities and dealing with some common pain points.
Right. So imagine you're sitting there with your data. Maybe you've got dozens, hundreds, I don't know, even thousands of potential variables. You run your first linear regression, but it feels clunky. Or maybe it's just not doing that well on new observations. What do you do then? That's really the core question we're digging into today.
Okay, let's unpack this a bit. We often start with the tried and true least squares method, OLS. It's like the workhorse of statistics. But under what conditions does it start to, falter? Why would we even look for alternatives? That's a great place to begin. OLS is robust, sure, but it does have specific limitations that our source material points out clearly. The first one is really about prediction accuracy. When you have a large number of predictors, let's call it P, especially if P is bigger than the number of observations, N, which happens more than you'd think, OLS can get really unstable. The estimates can have very high variance, and that leads to models that perform poorly when you try to predict new, unseen data. It essentially overfits the training data. It captures noise, not the real underlying patterns.
Overfitting,
Yeah.
Right. It knows the past too well, but can't predict the future.
Exactly. And the second big concern is model interpretability. Just picture a scenario with, say, hundreds, maybe thousands of potential explanatory variables. Even if your predictions are okay, trying to figure out which variables are actually driving the outcome becomes incredibly difficult, just a mess. We often want a simply more concise model, one where irrelevant features are effectively dropped by setting their coefficients to 0. That gives you a much clearer story about what's really important.
Okay, so it's about making our models smarter, easier to understand, and stopping them from just memorizing the training data. What's really interesting here is that the problem isn't always not enough information, but sometimes it's too much, or maybe just too much noisy information. And that's where OLS starts to struggle. All right, let's dive into our first toolkit then, subset selection. When we talk about this, is the idea basically trying to find the absolute best handful of ingredients for our statistical recipe.
That's precisely it. The core idea of subset selection is to find a simpler model using only a subset of the predictors you have available. The goal is usually twofold. Improve interpretability, obviously, but also potentially boost predictive performance on new data. And the most direct approach here is something called best subset selection.
Okay, best subset. How did that work systematically?
Well, it's systematic, but it's exhaustive. You start with what's called the null model, just an intercept, no predictors at all. Then, for every possible number of predictors, let's say k, from 1 up to p, the total number you have, you fit all possible models that contain exactly k predictors, all of them. From that huge list, you then pick the best model for each k. Usually best means the one with the smallest residual sum of squares, the RSS, or equivalently, the highest R squared.
Fitting all possible models sounds computationally heavy.
Oh, it is. That's the crucial detail and where it gets tricky fast. For P predictors, there are 2 to the power of P possible subsets you need to check. So if you have a fairly small data set, like the credit data set mentioned in the source, with 10 predictors, well, 210 is about 1,000 models. That's manageable.
1,000, okay.
But jump to just 30 or 40 predictors. 230 is over 1 billion. 240 is over 1 trillion. It just explodes. It becomes completely computationally impractical for many modern data sets.
Wow, okay. So best subset selection gives you the theoretical best, but it can quickly become impossible to actually run. So what are our practical alternatives, like the good enough shortcuts for picking our model's ingredients without waiting forever?
That's exactly where stepwise selection methods come in. They are much, much more computationally efficient. We're talking maybe around p-squared models instead of 2 to the p.
P squared versus 2 to the p. Big difference.
Huge difference. And there are two main flavors: forward stepwise selection and backward stepwise selection. Forward stepwise starts simple, with no predictors, just the intercept. Then it adds predictors one by one. At each step, it looks at all the predictors not yet in the model and adds the single variable that gives the biggest improvement to the fit. It's kind of a greedy approach, makes the best local choice now, but doesn't look back.
Okay, builds up from nothing. What about backward?
Backward stepwise does the opposite. It starts with the full model, using all p predictors. Then it iteratively removes the least useful predictor one at a time until some stopping rule is met, like maybe based on p-value or AIC. But there's a key requirement for backward stepwise. The number of samples, n, must be greater than the number of variables, p. You need enough data to even fit that initial full model.
Right. If Pn, the full model is unstable anyway.
Exactly. You can't even estimate it uniquely sometimes. And our source actually gives a neat example with that credit data. It shows that best subset and forward stepwise can actually end up picking different models as the best 4-variable model. This happens because of correlations between the predictors. It highlights an important point. These stepwise methods, they don't guarantee finding the absolute best model out of all 2p possibilities.
But they're practical.
They're practical, they're efficient, and honestly, they often perform very well in real-world situations.
Got it. So stepwise methods are like smart shortcuts. They navigate this huge search space much faster. But we have to remember they might miss the absolute perfect combination sometimes. It's that classic trade-off. Computation versus guaranteed optimality. Often a worthwhile trade-off. All right, let's switch gears. Let's pivot to a totally different philosophy. Shrinkage methods, or regularization. So instead of kicking variables out entirely, we fit a model with all the predictors, but we gently push their coefficient estimates towards 0. That sounds a bit strange if you want simplicity. How does that help?
Yeah, it might sound counterintuitive at first, but it's incredibly powerful. The basic idea is that by constraining or shrinking the size of the coefficients, we actually reduce their variance. Remember the bias-variance trade-off. By reducing the variance, even if we introduce a tiny bit of bias, we can often significantly improve the overall prediction accuracy, especially on new data the model hasn't seen before. It's like reining in predictors that might be getting a bit too enthusiastic based just on the training data.
Reining them in. Okay. So what's the first method here?
The first one is ridge regression. It works by minimizing the usual residual sum of squares, RSS, but it adds a penalty term to the minimization problem. This penalty is proportional to the sum of the squared coefficient estimates. We call this an L2 penalty, lambda times the sum of beta j squared. This penalty has the effect of shrinking the coefficients towards 0. It discourages them from getting too large. But a key thing about ridge is that it will very rarely force a coefficient to be exactly 0. They just get closer and closer as the penalty gets stronger.
So they get really small, but technically still there.
Exactly. And the tuning parameter, lambda, that Greek letter, is crucial. It controls how strong that penalty is. If lambda is 0, there's no penalty, and you just get the standard OLS estimates back. As lambda increases, the coefficients get shrunk more and more aggressively towards 0.
And you mentioned standardization.
Yes, that's a crucial practical detail for ridge. You really should standardize your predictors first, make them have mean 0 and standard deviation 1. Why? Because the ridge penalty treats all coefficients equally, but if your predictors are on vastly different scales, say one is dollars and another is years, the penalty will unfairly punish the one with the larger scale. Standardization puts them on a level playing field.
Makes sense. So ridge keeps all the players on the field, but kind of makes them play more conservatively, right? Moderates their impact. But my gut feeling is sometimes you really do just need to cut players who aren't contributing at all. Does any method do that? Does shrinkage ever actually remove variables?
Perfect timing. That leads us straight to the LASSO. That stands for Least Absolute Shrinkage and Selection Operator. LASSO also minimizes the RSS plus a penalty term, but instead of using an L2 penalty, sum of squares, it uses an L1 penalty. That means it adds lambda times the sum of the absolute values of the coefficients, sum of beta j.
Absolute values instead of squares. Why does that make such a difference?
It's fascinating mathematically and visually if you think about the constraint regions. The L1 penalty has this remarkable property. When lambda is large enough, it forces some of the coefficient estimates to be exactly 0.
Exactly 0. Not just close.
Exactly 0. Think about it geometrically. The L2 penalty, ridge, corresponds to a circular constraint region. It's smooth. The OLS solution usually won't hit exactly on an axis, but the L1 penalty, lasso, corresponds to a diamond-shaped region in 2D or a hyperoctahedron in higher dimensions. It has sharp corners that lie on the axis. It's much more likely that the optimal solution, where the OLS contours touch the constraint region, will happen right at one of these corners. And if it hits a corner on an axis, the coefficient for the variable corresponding to that axis becomes 0.
Wow. So Lasso does automatic variable selection.
Precisely. It performs variable selection as part of the fitting process. It creates what we often call sparse models where many coefficients are 0. So Lasso directly overcomes that disadvantage of Ridge, which always keeps all predictors in the model, even if their coefficients become tiny. Lasso can actually kick them out.
Okay, this raises the obvious question then. If Lasso can simplify the model by setting coefficients to 0, why would you ever choose Ridge? When does Ridge really shine?
That's a fantastic question, and it really gets to the heart of choosing the right tool. There's no single best answer. It depends on the underlying reality of your data, which you usually don't know for sure. Generally, Lasso tends to perform better when you believe the true relationship involves only a small subset of the available predictors. Think about it like this. If you're sifting through, say, hundreds of genetic markers trying to find the few that directly cause the disease, Lasso acts like a focused searchlight. It's designed to pinpoint those critical few and ignore the rest. Excellent for sparse problems.
Sparse problems.
Yeah. Ridge, on the other hand, might be better when you think many predictors actually have some effect on the response, even if those effects are small. Imagine predicting, say, stock market movements. It's likely influenced by countless economic indicators, news, sentiment, trading volumes, tons of things, maybe none dominating, but many contributing small amounts. Ridge acts more like a stabilizer. It keeps all potentially relevant factors in play, but dampens their individual influence, preventing any single one from having too much sway, especially if they're correlated. This often leads to more stable predictions in dense situations.
Dense situations where lots of things matter a little bit.
Exactly. Since you rarely know the true sparsity beforehand, what do? You use cross-validation, which we'll talk about later, to empirically test which approach, Ridge or Lasso, or even something in between like ElasticNet, works better for your specific problem.
Right. So it sounds like Ridge is maybe better for refining a complex system where many parts contribute, keeping everything balanced. Lasso is more for finding the star players and ruthlessly cutting the rest, focusing only on the biggest impacts, especially if you suspect only a few things really matter. Okay, on to our third class of methods. Dimension reduction. This sounds like we're still simplifying, but maybe in a different way. Instead of picking original predictors or shrinking them, we're transforming them, creating entirely new variables that are combinations of the old ones. How does that work?
You've got it. It's a fundamentally different approach. The core idea is that we take our original P predictors and project them down into a lower dimensional space, say M dimensions, where M is less than P. We then use these M new variables, these projections or components, as our predictors in a standard least squares model. This transformation can be really powerful, especially when your original predictors are highly correlated. By capturing the main patterns of variation in fewer, often uncorrelated components, we can often win big in the bias variance trade-off.
Fewer, less noisy variables. Makes sense. What's the main technique here?
The most famous and widely used dimension reduction approach for regression is principal components regression, or PCR. It's basically a two-step process. First step, you perform principal component analysis, PCA, on your predictor matrix, ignoring the response variable for now. PCA finds these new variables, the principal components, which are linear combinations of the original predictors. The key is that they're constructed to capture the maximum possible variance. The first PC captures the most variance, the second captures the most remaining variance while being uncorrelated with the first, and so on.
Okay, find the main directions of spread in the predictors. Then what?
Second step. You take some number, M, of these top principal components, the ones that capture most of the variance, and you simply use them as predictors in an ordinary least squares regression to predict your response variable, Y. The intuition is, if you have many correlated predictors, maybe like different measures of company size, a single principal component might capture that underlying size dimension effectively. The source gives an example with population and ad spending for different cities. Those are likely correlated. The first PC might represent some overall market size factor. PCR assumes that these directions of high variance in the predictor space are the important ones for predicting the response.
Assumes high variance directions are important for prediction.
Yeah, and that leads to a potential drawback. PCR is fundamentally unsupervised in how it finds the components. The response variable, y, the thing you actually care about predicting, plays no role in identifying the principal components. PCA only looks at the predictors, x. So there's absolutely no guarantee that the directions that best explain the predictors are also the best directions for predicting the response. A direction with huge variance might be totally unrelated to y.
Ah, I see. That feels like a potential disconnect. If our goal is prediction, shouldn't the thing we're trying to predict influence how we simplify our predictors? Seems like ignoring y could, I don't know, lead us down the wrong path sometimes.
You've hit the nail on the head. That's the exact motivation for another technique called partial least squares, or PLS. PLS is also a dimension reduction method. It also creates new features called components or latent variables that are linear combinations of the original predictors. But here's the key difference. Unlike PCR, PLS identifies these new components in a supervised way. It explicitly uses the response variable, y, during the component construction process.
Supervised dimension reduction. How does it use y?
It tries to find directions in the predictor space that not only summarize the predictors well, like PCR, but are also highly correlated with the response y. So when PLS computes its first component, for instance, it tends to place higher weight on those original variables that have the strongest relationship with the response. It seeks components that are simultaneously good summaries of x and relevant for predicting y.
That sounds much more targeted for prediction.
It does sound intuitively better for prediction, doesn't it? However, the source material actually notes that in practice, while PLS is appealing, it doesn't always outperform ridge regression significantly. Ridge is often very good at handling correlated predictors too, just through shrinkage. So PLS is another tool, but maybe not always a dramatic improvement over ridge or even PCR in some cases. It depends.
Okay, interesting nuance there. So maybe to summarize, PCR finds the main patterns in the predictors themselves, kind of understanding their inherent structure. Good for data exploration, maybe.
Yeah.
Whereas PLS specifically looks for predictor patterns that are linked to the outcome variable, more focused on the prediction task itself.
That's a great way to put it. PCR is about explaining x. PLS is about explaining x and y simultaneously.
Right. We've covered a lot of ground. These incredible tools for building better models. Subset selection, shrinkage methods like ridge and lasso, dimension reduction with PCR and PLS. But now the big question. With all these options, how on earth do we choose the single best model for our specific problem? It feels like we've got a lot of powerful but different choices.
This is probably the most critical part, and where people often get confused. You might think, okay, I'll just pick the model with the smallest RSS or the highest R squared on my training data. But that's a trap. The model with the smallest RSS or highest R squared will always be the most complex one, usually the full model with all predictors if you're doing OLS, or the one ridge lasso model with lambda 0, because those metrics measure training error, how well the model fits the data it already saw.
Right, the overfitting problem again.
Exactly. Our real goal isn't minimizing training error, it's minimizing test error. That is, how well the model performs on new, unseen data. And training error is notoriously bad, often a wildly optimistic estimate of test error, especially with complex models.
Okay, I follow that. So minimizing errors on the data we have isn't the same as predicting the future well. We need a more honest broker, something that estimates that future performance. What methods do we use for that?
Broadly, there are two main approaches to estimate test error and guide model selection. First, there are what we can call indirect approaches. These involve calculating certain statistics that adjust the training error to account for model complexity. You've probably heard of some of them. CP, MALO-CP, AIC, Akaike Information Criterion, BIC, Bayesian Information Criterion, and adjusted R squared.
AIC, BIC, adjusted R squared. Yeah, those ring a bell. How do they work?
They essentially take the training RSS and add a penalty that increases with the number of predictors in the model. The idea is to penalize complexity. For CP, AIC, and BIC, you want to choose the model with the lowest value, as this suggests the best balance between fit and complexity, leading to lower estimated test error. For adjusted R-squared, you maximize it, as it penalizes adding useless variables more than regular R-squared does.
So they try to estimate test error without needing a separate test set.
Pretty much. They provide a mathematical adjustment. And there are subtle differences. The source notes that BIC, for example, tends to place a heavier penalty on complexity than AIC, especially when you have a decent amount of data, like N7. This means BIC often favors simpler, smaller models compared to AIC or CP. It leans more heavily towards parsimony, echoing that idea of Occam's razor. The simplest explanation that fits well is often best.
Okay, so these are useful adjustments to training error. What's the other approach?
The second approach, often considered the gold standard, especially in machine learning contexts, involves direct approaches, namely validation set methods and cross-validation.
Ah, cross-validation. That sounds familiar.
Yeah, these methods provide a direct estimate of the test error. Instead of relying on mathematical adjustments and assumptions about error variance, they work by actually holding out some of your data. You train the model on one part of the data, the training set, and then test it on the part it didn't see, the validation or test set.
So you simulate predicting new data.
Exactly. The big advantage is that they make fewer assumptions. They work well even for very complex nonlinear models, where calculating things like degrees of freedom for AIC, BIC might be tricky. They directly measure out-of-sample performance.
How does it work in practice, say, for picking the number of predictors in subset selection?
Okay, so for subset selection, you'd perform your forward or backward stepwise procedure. For each potential model size, say one predictor, two predictors, etc., you'd estimate its test error using cross-validation. For example, in k-fold cross-validation, you split your data into k chunks. You train the model on k1 chunks and test on the remaining one, rotating which chunk is held out. You average the error across the k-folds. Then you just plot the estimated test error versus the number of predictors and pick the model size that gives you the minimum estimated test error.
Find the bottom of that U-shaped curve of test error.
Precisely. And there's a useful refinement called the one standard error rule. Sometimes the cross-validation error curve is pretty flat near the minimum. So instead of just taking the absolute minimum error model, you find that minimum error, calculate its standard error, and then you choose the simplest model, fewest predictors, whose error is within one standard error of that minimum. It prioritizes simplicity when performance is statistically indistinguishable.
That makes a lot of sense. Choose simpler if it's basically just as good. And does this apply to Ridge and Lasso too, for picking lambda?
Absolutely essential for Ridge and Lasso. Remember lambda, the tuning parameter that controls the amount of shrinkage. Cross-validation is the standard way to choose the optimal lambda. You try a whole range of lambda values. For each lambda, you fit the Ridge or Lasso model using, say, 10-fold cross-validation and calculate the average test error across the folds. You then plot the cross-validation error as a function of lambda and pick the lambda value that gives the minimum error. That's the lambda you use to fit your final model on all the data.
So cross-validation really is our workhorse here. It gives us the most trustworthy assessment of how well our model is likely to perform out there in the real world. It's about finding that sweet spot, powerful enough, but reliable, and not just fooling itself on the training data. Gives you real confidence.
Couldn't have said it better myself. It's fundamental to building models that generalize well.
Wow. What an incredible deep dive this has been. We've really journeyed through three powerful classes of methods for refining linear models. We had subset selection, like carefully picking just the right variables for the job. Then shrinkage methods, Ridge and Lasso, for taming those coefficients, with Lasso even doing automatic variable selection for us. And finally, dimension reduction, like PCR and PLS, creating entirely new, summarized features from our original data.
And crucially, we learned that picking the optimal model isn't about acing the test on the data we trained on. It's about robustly estimating how well it will predict on new data. Using direct methods like cross-validation is really key for that, often complemented by those indirect criteria like AIC and BIC that help us think about the balance between fit and complexity.
So what does all this mean for you listening right now? It means you've got a seriously powerful toolkit. You can build predictive models that aren't just accurate, but also interpretable, efficient, and reliable. You can really move beyond basic regression and start unlocking much more meaningful insights from your data, letting you make decisions with, well, hopefully, a lot more confidence. So here's something to maybe mull over. In this world that's just drowning in data, where predictive models are shaping decisions in everything, from healthcare to finance to, well, everywhere, how might the careful application of these kinds of model selection techniques, thinking critically about bias, variance, sparsity, and validation, how might that reshape the very questions we ask of our data? Could it lead us not just to better predictions, but maybe to entirely new and surprising insights about how things work?